I'm Dr. Sreedevi from IARE College, Hyderabad. Today we are going to see the graph theory review of basics 2. Today we will be discussing some topics on trees. The concept of tree is probably the most important concept in graph theory, especially in the area of applications. Here we will be going to discuss the basic concepts of trees, forests, sundows and centroids of a tree, and rooted tree. The spanning tree, minimum spanning tree, and its applications we will be discussing on next lecture. So we will see now what a tree is. I think I have already told you this graph theory is based related to our day-to-day life. Here we know what is a tree. We know that it is tree something like this. It is going on like this, right? So here we are going to see how a tree is. Look. Tree in a graph. We say that tree is a connected graph without any circuits. This is a connected graph and without any circuits. What is this circuitless graph? Yeah, what is this circuit? Circuit, when a path, first before that going to start with circuit, we will see what a path is. Then we will see what a circuit is. A path is an alternating sequence of vertices and edges. That is, if G has a vertices V1, V2, V3, etc., Vn, and edges E1, E2, E3, E4, etc., En. Then a path will be V1, E1, V2, E2, V3, E3, and so on, En, Vn. In this path, this is alternating sequence of vertices and edges. When it is path, these vertices will not be repeating. If both this Vn is called the initial vertex of the path and Vn is called the terminal vertex of the path. If both Vn equal to Vn equal to V1 equal to Vn, then we say that it is a closed path. And closed path is also sometimes called a circuit. Okay. So, a path is an alternating sequence of vertices and edges, and if where the vertices will not be repeating. And if it is a closed path, then we refer that path to be a circuit. Now, we will see what is a tree. A tree is a connected graph without any circuits. Here, when it is V1 equal to Vn, how the path will be? That is, we will be starting with vertex V1, then we will be going to edge E1 to through E1 to V2. From there, we will be going to V3 through E2 and so on. When it is equal to Vn equal to V1, this we will be getting this as Vn. Okay, that is it can be also termed as a cycle. So here, that is a circuit can also be termed as a cycle. So a tree is a connected graph without any circuits. Can you find any closed path between these vertices? If you are starting from this vertex, can you reach back to that vertex? No. So the graph is said to be a tree if it is without any circuit. That is, there is no closed path in a tree. Suppose we are drawing like this. Then will it be a tree? Because we can find a closed path connecting these vertices. So this is not a tree. Okay. A tree with one vertex, because we know if a graph is to exist, there must be at least one vertex. In the same case, in the case of tree also, a tree with one, so there must be at least one vertex for a tree. So a tree with one vertex is this, a tree with two vertices is this, 3, 4 vertices are like this. Okay, a tree with 4 vertices. If I am drawing on one more edge, parallel edge, will it be a tree? No, because we have got a circuit connecting these two vertices. That is, if this is V1 and this is V2. And if you are connecting one more edge through this, then it forms a parallel edges. And this will be making a circuit, which is not. So this is not a tree. Also, if I am putting one more edge here, then it is a graph with circuit connecting these vertices. So it is not a tree. Okay, so this is a tree with 1 vertex, 2 vertices, 3 vertices and 4 vertices. From the definition of tree, it follows that simple graph without, it should be, from definition of tree, it follows to be a simple graph without any loops and multiple edges. Now we will see where these trees appear in our real life. Actually, the tree we will be using is family tree. We are all familiar with the family trees. The genealogy of family is represented by means of a tree. Actually, in graph theory also, this term tree came from this family tree itself. And the river and its tributaries can be represented by its tree structure. Also, when coming the primitive example where we were using these trees were the sorting of males according to the zip code and sorting of punch cards. And we will see this one of the example where the sorting of letters were being done. Suppose this all the mails are coming to one post office. And this because there will be, even though we are having 5 digits in a zip code, we have combination of 10 letters from 10 digits from 0 to 9. So all the mails coming to local post office, most significant digit in the zip code is read as N, and the mails will be divided into 10 piles, letting naming to be N0, N1, N2, etc. N9, N9, depending on the most significant digit. Each pile is further divided into 10 piles according to the second most significant digit, and so on till the mail is divided into 10 raised to 5 possible piles, and each representing a unique digit of the 5-digit zip code. And the tree structure will be like this. See here, it is N, where the let it be the first coming post office from where the mails are being divided. There's from the first significant digits will be sorted to N0, then N1, N2, N3, etc. We will be sorting it to N9. Again, this each points will be divided to 10 points. That is, from here N0 we can divide it into again 10 points. N0 we can divide it into 10 lines. As it is because of the constraint of space, I am not drawing all those. From N0 we can divide it into 10, N1 we can divide it into 10, and so on. From N9 we can divide it into 10. Next, that is second significant digit in the zip code. So we will be continuing like that. A tree structure will be called. Same cases happen in the case of punched card sorting also. In many sorting problems, we have only 2 alternatives. Because in case of this zip code posting and all, we will be having 10 possibilities. And in many cases like that, sorting problems, we will be having 2 possibilities sorting, such as large or small, yes or no, 0 or 1, and so. So such a decision tree with 2 choices at each vertex occurs frequently in computer programming and in switching theory. Some simple properties of trees. There is one and only one path between every pair of vertices in a tree. What will happen if we have got 2 pairs of 2 paths? Then occur this union of these 2 paths will form a circuit, and this resultant graph will not be a tree. Then if in a graph G there is only one path between every pair of vertices, then that graph is termed to be a tree. It is a graph is said to be a tree if there is only one path between every pair of vertices. Simple properties of trees. There is one and only one path between every pair of vertices in a tree. As a tree's connected graph, there should exist at least one path between every pair of vertices. I think I have told you what is connected graph and disconnected graph. A graph is said to be connected if there exists at least one path between every pair of distinct vertices. Suppose if in a tree there exists two paths between distinct pair of vertices, then the union of these two paths will form a circuit and the resultant graph will not be a tree. Then we can say what happens a graph, when and where a graph can be said to be tree. If there is only one path between every pair of vertices, then it is termed to be a tree. A tree with n vertices has n minus 1 edges. Is it so? Let us see our first example. Here how many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, 19 vertices. How many edges are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. What will happen if I am adding one more edge? If I am adding one more edge, arbitrarily I am just adding one more edge. Will it be a tree? No. So, in a tree with n vertices, if a tree has n vertices, it has n minus 1 edges. Okay. So, look at this. A tree with n vertices has n minus 1 edges. Any connected graph with n vertices and n minus 1 edges is said to be a tree. If we are given a graph and if it has n vertices and n minus 1 edges, we then term it to be a tree. A graph is tree if a graph is a tree if and only if that it is minimally connected. What is this minimally connected? Even if we remove one edge from that tree, it will be disconnected. Suppose if I am removing this edge from this tree, what will happen? This portion, that is the tree pot, this part emerging out of this and not from the second set, will be disconnected from entire graph. That is, a tree is a minimally connected graph. A graph with n vertices and n minus 1 edges and no circuit is connected. If we are given a graph n of n vertices, that is, order of the graph is n and size of the graph is n minus 1 and it has no circuits, then the graph will be automatically connected. From these basic properties of trees, we can give five different but equivalent definitions of a tree. Let us see what it is. A graph G with n vertices is called a tree if G is connected and circuitless. What it is? G is connected and circuitless. Next one is G is connected and has n minus 1 edges. That is, a graph with n vertices is a tree if G is connected and has n minus 1 edges. Next one, a graph with n vertices is called a tree if G is circuitless and has n minus 1 edges. Else we can say that a graph G with n vertices is called a tree if there is exactly one path between every pair of distant vertices of G. Okay. Or else we can say that graph G with n vertices is called a tree if G is minimally connected graph. So these are all the 5 different but equivalent definitions of tree. If anyone is saying that G is minimally connected graph, G is a graph with n vertices is a minimally connected graph, then it is a tree itself. We cannot say that only one definition is enough for a tree. These are all 5 equivalent but different definitions of tree. What is pendant vertex? I think you all know the degree of a vertex. Number of edges incident on a vertex is termed as degree of a vertex. V. If V is a vertex, then how many edges are incident on that V refers to be the degree of a vertex. If degree of vertex equal to, if the degree of vertex V is 1, then we refer this vertex to be a pendant vertex. That is n vertex. Pendant vertex means another name for pendant vertex is n vertex. That is from the terminology itself, it comes to know that it is up to the end of something. Okay. In any tree with 2 or more vertices, there are at least 2 pendant vertices. Suppose I have any tree with 2 vertices. So how many pendant vertices here I am having? Yeah, we have only 2 pendant vertices. Suppose I am going to draw a tree with 3 vertices like this. This is a tree. How many pendant vertices? 2. If I am having graph with 4 vertices, tree with 4 vertices, it is a tree with 4 vertices. Right? It's a tree with 4 vertices. How many pendant vertices? I am having 3 pendant vertices. Graph with tree with 4 vertices, and here I am having 3 pendant vertices. I can have another graph also. It's a tree with 4 vertices. How many pendant vertices? 2. So in every tree with at least 2 vertices, it will have at least 2 pendant vertices. Application of trees. We have been applying trees in many sorting problems. Here we will see how a tree is used in one such sorting. Given a sequence of integers such that no two which of are same. Find the largest monotonically increasing sequence in it. What is monotonically increasing? Yeah, even it is coming to that first term, second term will be increasing from the first, third term will be increasing from the second, and so on. So we have to find such a sequence from that. Suppose the sequence given to us is 4, 1, 13, 7, 0, 2, 8, 11, 3. We have to find a different monotonically increasing sequence from that. The easiest way we can find from here, one by one we can try and write. This is a small sequence with how many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, only 9 digits. So we can directly apply it. We can see and say how many digits how many sequences we can write. But when it comes to give n number of terms, what we will do? We will see with the example of this small sequence. Okay. It can be represented as a tree, starting with a vertex, with vertices starting at some, just you give a node, and each then from that node you just start every numbers. From that numbers we can like that a path from a vertex, start vertex to a particular vertex V describes the monotonically increasing sequence by terminating at V. We will see here. We are putting at a start vertex here, and we are putting each numbers of our sequence 4, 1, 13, 7, 0, 2, 8, 11 and 3. From here we can see that from 4, how many numbers are increasing from 4? It is 13, 7, 8 and 11. Okay. Then from 7 we know that after 7 it comes 8. So after 8 it comes 11. And we are drawing like tree structure like this. From 8 from 7 next number increase. One is 8 and one is 11. So 11. From is there a number greater than 11 in that sequence? No. So we cannot go to that. In the same manner, we are starting from 1. We have the numbers which are increasing from 1 as put in the next level. Then from each level, this 7, 2. From 2, we have 8, 11, 3. Okay. Which are numbers greater than 2. From this 8, we can go to 11. From 11, can we go to any other number? Because no. Because there are no numbers which is greater than 11 in this sequence. So we are continuing like that, and we will be getting how many sequences of longest length? This. Because 1, 2, 3, 4 level. 1, 2, 3 and 4. Here also 1, 2, 3, 4. 1, 2, 3, 4. So we will be getting, from the figure we can see that there are 4 longest monotonically increasing sequence, which are, because from the figure here we get 4, from 4 we will be getting 4, 7, 8, 11. From 1 we are getting 1, 7, 8, 11 and 1, 2, 8, 11. Okay. Can we put this to be monotonically increased for long lengthy sequence? No, because we have here only of 3 length. Here we have another one of 4 length, 0, 2, 8, 11. Okay. So we got 4 sequences. This 4, 7, 8, 11, 1, 7, 8, 11, 1, 2, 8, 11, 0, 2, 8, 11. This 4 sequence. As it is a small sequence, we could complete it in this way. If there were so many numbers in the sequence, we should have gone through. The tree structure will be much more complicated, and I hope you will be able to do that. Such a tree used in representing data is referred to as data tree by the computer program. Such a tree used in representing data is referred to as a data tree by computer programmers. Now we will see what a forest is. We know in our real life condition what is a forest. Real life situation, we are in a forest, we know there is plenty of trees. There are plenty of trees in a forest. So here also when it comes to forest in graph theory, forest is a graph that contains no cycles and a connected forest is a tree. In other words, we can say that a forest is a collection of trees. Here we can see that it is a forest of 4 components. Here each component is a tree. Is it so? Yeah, this component is a tree. This is a tree with 4 vertices and 3 edges. This is a tree with 3 vertices and 2 edges. And this is a tree with how many vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices and 8 edges. If I am connecting these trees through an edge, how this? Yeah, I'm just arbitrarily drawing. Is the resultant graph a graph with any circuit? No. The resultant graph is again a tree. So forest is a graph that contains no cycles. And the connected forest is a tree. Also, it can be termed as a collection of trees. The forest is a collection of trees. And this forest is a graph that contains no cycles and connected forest is a tree. Okay, here the forest has 4 components and each component of which is a tree. Just remember. Now we will see what is center and centroid of a tree. Before to know the center, centroid and all, we should know the distance between 2 vertices. The distance between 2 vertices is termed as the number of edges occurring in the path between 2 vertices. That is, if this is V1, V2, V3, V4. And the distance between this V1, V3 is 2. How? There are 2 edges happening between these 2 vertices. There are 2 vertices occurring in the path between V1 and V3. So the distance between V1 and V3 is 2. Sorry, distance between V1 and V3 is 2. And what about the distance between V1 and V4? It is 3. Okay. And what is the maximum distance of V1 with any other vertex? It is if it is distance between V1, V2 is 1. Distance between V1, V3 is 2. Distance between V1, V4 is 3. So with which vertex the distance is, with which vertex the vertex V1 is at a maximum distance? V1 is at a maximum distance with V4, right? Now we will see what is the eccentricity and all. The eccentricity of a vertex V in a graph G denoted by E of V is the distance from V to the vertex farthest from G. It is the distance which is far away from V. So eccentricity of V is the maximum of distance between V and VI, where VI is any other vertex in the vertex set of G. Okay, that is, here we have seen that E of V1 equal to 4 because, E of V1 equal to 3 because V1, the distance between V1, V2, V3, V4 and E of V1 equal to 1, 2, 3. It is because it is the maximum distance of V1 from any other vertex. As it is a simple path, we can find like that. What happens if graph is like this? V4, V5, V6. We can find the distance between V1 and V5 to be 2. And also the maximum distance between V1 and V5 is 1, 2, 3, 4. Okay. So maximum distance between V1 and V5 is 4. It is minimum distance between V1 and V5 is 2. So eccentricity of V1 is E of V1 is 4. Okay. A vertex with minimum eccentricity in a graph is called the center of the graph. A vertex with, we have to find the eccentricity first, which is the maximum of the distance from that particular vertex to any other vertex in the graph, and a vertex with minimum eccentricity is termed to be the center of the graph. Consider the graph with eccentricities of each vertex marked against the vertices, corresponding vertices. Here, if this eccentricity of A, what is the eccentricity of A? We can find that A is at a maximum distance from, is it with B? Because early distance between 2. And what about A and C? Its distance is 2. And what about A and D is at 2. So eccentricity of A is at the maximum distance means 2. What about the eccentricity of B? B is at a distance of 1 from every other vertices. So maximum distance is also 1. So the eccentricity is 1. And C is at a distance of 1 from B and C is at a distance of 2 from A and D. So the maximum of the distance of C from a farthest vertex is 2. So it is eccentricity of C is 2. And here hence with the same conditions, eccentricity of D is 2. And vertex with minimum eccentricity, yeah, it is D. It has to be put equal sign. Yeah, it has to be, eccentricity should be minimum. A vertex with minimum eccentricity is termed to be the center of graph. Now consider these trees T1, T2, T1, T2 and T3. The eccentricity of each vertex is marked against the corresponding vertex. Now here I have marked 6. Why? Because from here we can find the farthest root 1, 2, 3, 4. It is the, when we are thinking about this vertex, it is 4. 1, 2, 3 only here. 1, 2, 3, 4, 5, 6. So it is the distance of this vertex to the farthest vertex is 6. And what about this vertex? We are considering this path 1, 2, 3 only. Here 1, 2 and here 1, 2, 3, 4 and 5. And this vertex 1, 2 here also 1, 2. When we are going to consider this path 1 only and here 1, 2, 3, 4. So here goes the eccentricity of this vertex to be 4. And what about this vertex? Here we are taking this path 1, 2, 3 or 1, 2, 3. Here 1, 2, 3. Here also 1, 2 and here 1, 2. 1, 2, 3 here and here 1, 2. So the maximum distance from this vertex to the farthest vertex is 3. Here it comes to be 4 and here it comes to be 5 and here it's 6. So this is the vertex with minimum eccentricity and so it is termed to be the center of that vertex. So I hope the eccentricity and center is familiarized. Here also what happens? This vertex is the center. Why in T2? Because from here we can go through these 2 vertices here only. Here, 2 edges distance is 2 and here also the farthest distance is 2 and here also the farthest distance is 2 and it is the farthest distance is termed to be 2 and it is here from here in this figure we have 4, 4, 3, 2, 3 and 4. So vertex with minimum eccentricity is this vertex with eccentricity 2 and it is the center of the graph. Here also we have, from here if we are starting, we can see that the eccentricity is 2. But when we are starting from this vertex, we can see that the eccentricity is 1. So it is termed to be the vertex. Center of the graph. And from here we can see that there are 2 vertices with same eccentricity. So can we term to be the center of that? Can we term those 2 vertices to be the center of that tree or center of that graph? Yeah. The vertices with minimum eccentricities are termed to be the center of the graph and we can see that whenever these 2 centers occur, they are adjacent to each other. We can see some results on the center of graph, centers of trees. Every tree has either 1 center or 2 center. Because from these definitions, we have seen that every tree has at least 1 center. In some cases, there may be 2 centers. If a tree has 2 centers and 2 centers must be adjacent. The eccentricity of a center in a tree is defined as the radius of the tree. Eccentricity of the center. That first we defined what is eccentricity, then we saw what is center of a tree. The vertex with minimum eccentricity is termed to be the center of the tree. And the eccentricity of the center is termed as the radius of the tree. And diameter of the tree is defined as the length of longest path in tree. So what is the radius of this tree? First T. Here the radius of this T, equal to 3. And what about the diameter of that tree? It is the length of longest path, right? So diameter of this tree is 6. And what about here? Here the radius of radius of T1 is 2 as it is the eccentricity of the center. And what about the diameter of this T1? It is 4. And what about in T2? Radius of T2 is 1 and diameter of T2 is 2. So it's like in circle also. When we are saying about circle, the radius is half the diameter, right? Can it be true in the case of trees? No. Consider this tree, T3. What is the radius of T3? It is 2. And what about the diameter of T3? It is 3. So in a tree, the radius need not be half the diameter. Okay? Radius in a tree, see that remark, radius in a tree is not necessarily half its diameter. Now, next important concept in tree is the centroid of a tree. Usually we know the centroid, centroid means the particular center from which we can, if we are putting the plane figure in, we can point with a single point. We can balance that figure with a single point. Here what we will see, what is the centroid of a tree. In a tree, at every vertex of degree D, there are D subtrees with only vertex V in common. That is, if you are having a vertex with degree 3, we can subdivide it into 2 subgraphs from one here, that is V1, V2, V3, V4 and V5 and V6. we can put it into V1, V2 and V6, V2 and V2, V3, V4, V5. So, in a tree, any vertex V of degree D can be divided into D subtrees. Here, vertex with degree 3 can be divided into 3 subtrees. So, vertex with degree 3 can be divided into 3 subtrees. Okay? With vertex, particular vertex of degree 3, here it is V2 and V2 as common, we can divide it into 3 subtrees. The weight of each subtree at V is defined to be the number of branches in the subtree. So when we were considering this tree, this V6 here V2, V3, before that here V1, V4. When we are considering this, when I am considering the division of this tree, this at V2, I can divide it into 3 subtrees, right? V1, V2, one subtree, and another one V6, V2, and another one V2, V3, V4. If it is T3, T1, T2 and T3. This T1, T2 and T3. The weight of each subtree at V is the number of branches in the subtree. That is, here the weight of this subtree at V2 is 1. Here it is 1. And what about here? It is 2. Okay. The weight of each subtree at V is the number of branches in that subtree. The weight of the vertex V in this original tree is defined as the weight of the heaviest of the subtrees at V. So what is the heaviest of the subtrees here? Here it is with 2 branches. So weight of this V2 in this graph is termed to be 2. The vertex with smallest weight in the entire tree is termed to be the centroid of T. And we will see here. Consider these trees whose weights according to each vertex are marked near to that vertex itself. Here when we are dividing it into, here we can divide this vertex into subtrees, 3 subtrees, because why? This vertex has weight, this vertex has degree 3 and it can be divided into 3 subtrees at this point. Okay. So the maximum weight of the subtree will be this with, if we are considering this subtree only, it can be 1, here also 1, and this subtree consisting of these portions, the weight of that vertex, weight of that vertex means weight of the heaviest of the subtrees. The weight of the heaviest subtree is here 1, 2, 3, 4. Weight of a subtree means number of branches occurring in the subtree. And weight of the heaviest subtree is here 4. So the weight of the vertex is marked as 4. And here where the weight of the heaviest subtree is 3. And here the weight of the heaviest subtree is 5. Here it is 6. So weight of the subtrees. And here we are defined the centroid of a vertex to be the vertex with smallest weight in the entire tree. So here the vertex with smallest weight in the entire tree is this vertex with a degree. Sorry, weight. It is not the vertex with not only the vertex with a degree 3. It is the vertex with weight 3. When we are considering, when we are putting why I have put this 4 here, why this 6, it is not the distance nor the degree of the vertex. It is the weight of the vertex. And weight of the vertex means it is the number of branches occurring. Weight of a vertex means number of branches occurring in that. And weight of a vertex means the weight of the heaviest subtree. Okay. And weight of the heaviest subtrees containing this vertex is, everything is marked like this. And vertex with minimum weight is termed to be the centroid. And the vertex with minimum weight is here. The vertex with minimum weight is 3. And it is termed to be the centroid of the vertex. Also here, when we consider these vertices, you can see that it is of degree 2 only. Then don't confuse with this weight and degree, nor with the distance. weight, degree, distance, everything are entirely different concepts. Okay. Here we are getting a vertex with weight 4 here, and here also we are getting a vertex with 4 here. So these two are centroids of a tree. So we have already seen that a tree can have tree must have at least one center. At the same, in the same manner, a tree must have at least one centroid. And when in the earlier we have seen a tree may have two centers. There also we are seeing that a tree may have two centroids. And there we have seen that when tree has two centers, that centers will be adjacent. Here also we have seen that when tree has two centroids, they will be adjacent vertices. Okay. This is what I have told. As in the case of centers of a tree, every tree has either one centroid or two centroids. If a tree has two centroids, they will be adjacent like in this case. In some authors have referred a centroid of a tree to be a knot whose removal from the tree will split into a forest, such that any tree in that forest will have at most half the number of vertices in the original tree. That is a knot which when is removed from the tree, it will be split into forest. Forest is a collection of trees. When components of forest are connected by single edges, then it forms a tree. Okay. So centroid of a tree can be defined as a knot whose removal from the tree would split it into a forest, such that any tree in particular component of the forest would have maximum half the number of vertices in the original tree. Here let us see. Here we have this vertex with weight 3 to be the centroid of the tree, right? When I am removing this vertex, if I am removing that vertex, what will be the resultant trees? It will be like that only, no? How many vertices we had in this tree? 1, 2, 3, 4, 5, 6, 7. How many vertices in each component? Here we have, it is 3, here it is 1, here it is 2. Is there any other? It is less than half the number of vertices in each component. Number of vertices in each component is less than the number of vertices and less than half the number of vertices in the original graph. Okay. When we are considering this graph, what will be the effect? How many vertices we have here? N equal to 1, 2, 3, 4, 5, 6, 7, 8. If I am removing this component, okay, what is the maximum number of vertices on each first component? 1, 2, 3, 4. And here we will be having 1, 2, 3. They are two independent. Sorry, one component here, and this. It will be like that. Suppose I am removing this, I am going to remove this only. Okay. This tree will split it into how many components? We will be having it into this one component, and other components will be like this only. Right? And how many vertices are there? Here we have 4. And how many here? 1, 1, 1. So, the number of components, number of vertices in each component is at the maximum, it can be half the number of vertices in the original graph. That is what here. Centroid of a tree can also be defined as a knot whose removal from the tree would split it into forest, such that any tree in the forest would have at most half the number of vertices in the original tree. Okay, now we are going to some other important concept of tree. It is rooted tree. What is rooted tree? A tree in which one vertex is distinguished from other vertices is called a rooted tree. While we were considering this sorting problem, here this start vertex is different from all other vertices in this graph, right? From here we are starting. And before that, many thing happens. From here, we are going to start. And so it is distinguished from, it's on what priority. So it is distinguished from other vertices. So it is termed to be a rooted tree. Here, when we are considering this letter sorting problems, this post office where all the letters come in, from where it is being disposed, this graph, this point is termed to be the root of that tree. Okay. A vertex one which is distinguished from all other vertices, then it is termed to be the root of that tree. And the examples, first the mail sorting problems, and when considering the monotonically increasing sequence, the start vertex which we consider can be considered as the root of the tree. And in a rooted tree, some important definitions which I am defining is given in bold letters. In a rooted tree, the level or depth of a vertex is the length of unique path from root to V. That is, when we were considering that letter start, from there we went to 0, from there we went to 2, and from there we went to 8, from there we went to 11. Okay. And this is the, this 11 is at a level 1, 2, 3, 4. Okay. So that is the level, depth of a vertex is the length of unique path from root to the particular vertex, or level of a particular vertex is the distance of the path from root to that particular vertex. Level, it can be termed also as depth of a vertex from the root. And is the root at the root? It is at level 0. Height of a tree is the length of longest path from the root. So in our other number sequence, the height of the tree was 4. Okay, length of longest path from the root is termed to be the height of the tree. If a vertex V immediately precedes a vertex, if a vertex U immediately precedes a vertex V on the path from root to V, then U is called the parent of V, and V is called the child of U. So in our case, we had the 0 from root. Here we are, that is start. From there we had 0. From there we went to 2. From there we went to 8. From there we went to 11. Okay. So 0 is, here the vertex at 0 is said to be the parent of 2. And 2 is called the child of 0. And 2 is the parent of 8. And 8 is the child of 2. And here 11 is the child of 8. Is 11 a parent of anyone? No. Okay. And we here, this 8 is called also termed to be this vertex, if it is vertex U. If it is V and U, then U is called the parent of V and V is called the child of U. And V is also termed as descendant of U, and U is called the ancestor of V. As when we were using the family trees and all, first from ancestor, then we'll be going to next descendant, right? The same way, all the name terminologies have been given here. A leaf in a rooted tree is a vertex having no children. Here, in our considering 0, 2, 8 and 11. Here, 11 is said to be a leaf. Here the vertex 11 coming on that point is said to be leaf. A leaf in a rooted tree is a vertex having no children, and any internal vertex in a rooted tree is any vertex that is not a leaf. That is, here it is internal vertex 8. But in another case we have start from the start we have gone to 11 itself. Here 11 is a leaf only. Okay. And from there, in the case we went to 11. Then in some cases we went to 8, 11. Here 11 is leaf, 8 is an internal vertex. Okay. An emerald tree in a rooted tree is if every vertex has less than or equal to m children. If every vertex has less than or equal to m children, then that rooted tree is termed to be a emerald tree. A complete emerald tree is that in which each internal vertex has exactly m children. When this m is equal to 2 and 3, the corresponding emerald trees are called binary trees and ternary trees respectively. We will see that. This is a ternary tree. Why? Because this we can call it to be a three-arrayed tree. Why? Because every vertex here, this vertex has maximum of 3 children. And here it is 2 children. Right? From here we are getting this, if it is root, from root we are getting 3 children. This is the parent of this vertex, these 3 vertices. This vertex can be termed, if it is V, V1, V2, V3. V1, V2 and V3 are children of this vertex V. And it has maximum 3 children. So it is a, from here V1 has 2 children. Let it be V11, V12. Here V2 has 1 child, V21. And V3 has how many children? 3 children. So V31, V32, V33. And here V32 has 1 child. So I'm going to put it as V321. Because there's suffixes are like that only. From V1 we got these 2. From V2 we got this one. From V3 we got these 3. And out of that, next level is this one. Okay. I hope you can familiarize it to be some family trees itself. So here maximum 3 children happen. So it is termed to be a 3-array tree, which can be called as ternary tree. Here look at this vertex. It has 2 children. From here also these 2 children are having 2 children. 1, 2, 1, 2. And again these 2 children are having these 4. If it is father, son, their grandchildren, then they again are having 2s. That is every vertex is having 2 children. That is every internal vertex is having 2 children in the next level. So this is internal vertex when these are all internal vertex. And every internal vertex is having 2 children. Then this tree is called complete 2-array tree, or complete when 2-array is coming, it is termed as binary tree. So it is complete binary tree. Okay. Binary trees are widely used in computer search methods, binary identification problems, and variable length binary codes. While coming to binary codes and all, if we are starting like that from this, if it is gone to here 1 and here 0, from here we can write it as 0, 1, and here it is 0, 0. And from here we can go to as 0, 1, 1 and 0, 1, 0. And so that it can be represented for representing the binary length, variable length binary codes. And also for binary identification problems and binary search methods. Okay. And so here we call it as level 0. If it is level 0, that is root. Then it is level 1. And from here level 1 we are getting to level 2. Here is level 2. Here is also level 2. From level 2 we are going to level 3. Okay. Here also we are going to level 3. Here also we are going to, these are all at level 3. And from here we are going to level 4. If I am having any other vertex from here, if I am going like this also at level 4. That is from root how we are going 1. So it is level 1. Here 1, 2. So it is at level 2. So a level means the depth. It is the length from the length of longest path from a root to the particular vertex. So I hope this level concept of the tree is binary tree level, depth, height, then emerald tree, everything is okay. Now we have considered this, what all we have done. Trees, tree, a graph is a graph G, connected graph G. If what happens, if it is a disconnected graph, then we will be getting forest only. Okay. A graph G, connected graph G with n vertices and n minus 1 edges is said to be a tree, and it is a circuitless graph. And what are the definitions of tree? I hope you all remember that. A connected graph G with n vertices, n minus 1 edges, and circuitless graph, and so on. And application of trees. Earlier we used trees for this sorting problems and all. Now these trees are representing this computer programming, and you are using this search methods. We will be using these applications. We will be going on in next series. And forest means collection of trees. Same thing in the real life. Forest means where we can see much more trees. In forest we see many more trees. So the forest is a collection of trees, or a graph when it is a collection when it is disconnected. When it is connected, we can get a trees. Okay. Then eccentricity. What is eccentricity? First we saw what is the distance between two vertices, and the eccentricity is the maximum distance between a particular vertex and the longest farthest vertex from that. And what is eccentricity? And we saw that what is center? Center means the vertex with minimum eccentricity, and what is centroid? The removal of vertex which disconnects the graph into tree, and such that the number of vertices in particular component will be less. Will be max at the maximum half the number of vertices in the original component. And what is rooted tree? And what it is rooted tree, and when it is and the concepts regarding the rooted tree like height, depth, then children, ancestor, everything. I hope it is all familiar with you. And thank you for watching this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.